Good morning, everyone. Welcome to week 5, our 5th week of Advanced Steel Structures course. Today we will go through the second part of the flexure member design. In last week, we designed the moment capacity of the member, the flexure members, and today we will go through the shear capacity and bearing capacity of the members. And I will start sharing the PowerPoint now. Okay. Can you see the PowerPoint? Can you confirm, please? Okay, thanks, Fatil. So today, our topic about the shear and bearing capacity of flexure members. Okay, so shear and bearing capacity for flexure members. So after today's lecture, you will be able to arrange stiffened and unstiffened webs for flexure members. This means that we will be able to know the dimension for web. So our topic today will be focusing on the web because the shear and bearing mainly depend on the web properties. So we have two types of webs, stiffened web and unstiffened web. Okay? And we will see now what is the difference between stiffened web and unstiffened web. And the second part or the next information we will learn today is how to determine or design the member for shear, or how to determine the shear capacity for stiffened and unstiffened web according to Australian standard AS4100. All our formulas and our data come from AS4100. And the next part is the shear capacity. Sorry, after the shear capacity, we have the bearing capacity of stiffened and unstiffened web. And the last one is how to design the different type of web stiffeners. So our topic today, shear capacity, bearing capacity, and how to design the stiffeners that enhance the shear and bearing capacity. So before we start, let's have a look on the girders webs. So the blade girder is a built up beams or girders designed to carry heavy loads over large span. So blade girders, if we are using blade girder like the one in this photo or this photo, so the blade girder is like blades welded together. For example, like that, to form I-beam or steel structure steel beam like that, because the load applied to this beam, heavy load, and we need to cover large spans. So in some cases, if we have heavy load and large span, we don't have enough section from the table like UB or UC or whatever or welded beam. So we need to sometimes to create the section ourselves. So this is the blade girders we are talking about in this slide. These girders are usually designed with deep and slender webs. As you can see here, the web is deep and cylinder. So if it's deep and cylinder, so it is susceptible to buckling. So that's why stiffeners are needed to enhance the shear capacity and the bearing capacity of the web. So let's look to the one on the left. It is unstiffened web, so the web stands alone without any stiffener or any support. If we look to the one to the right here, stiffened web, so again we have cylinder web, but we have supported the web with some stiffeners. We have two types of stiffeners. The first one is transverse stiffeners, which is vertical or parallel to the web, as you can see, if this is the web, so it is vertical. And we have another type, which is this one here, so it is longitudinal, because it's running with the web, or running longitudinally with the web. So our class today will be how to find the shear and bearing capacity for both unstiffened and stiffened web. Which one you expect has high or more shear and bearing capacity? The stiffened web girder, because we use the stiffener to increase the shear and bearing capacity. Okay? Do you have any question up to now? Okay. So our first part today will be arrangement of the web or the dimension of the web. So let's start with unstiffened web. For unstiffened web, the thickness of unstiffened web bounded on both longitudinal sides by flange shall not be less than this value. So T web in this case should be more than or equal to D1 over 180 multiplied by root F yield divided by 250. So if we see that, so this is T web here, and this is D1. D1 is the critical, is the clear depth of the web. Okay, so for unstiffened web, the thickness of the web cannot be less than this value, or T web should be more than this value, where D1 is the clear depth of the web between the flange, ignoring the willet, the fillet, or wheels. So this is the clear depth as we see in this image or this photo here, and T web is the thickness of the web. This for webs bounded on both longitudinal sides. Okay. The thickness of unstiffened web bounded only on one longitudinal side. The value should be doubled. So the value of the T web, the thickness of the T web should be D1 over 90 times F yield over 250, where D1 is the clear depth of the width again, of the web again. Okay. So this is the thickness, our most common or the common thickness we are using, because usually we are designing sections that have flange on both sides. So this is our TW, or the thickness of the web we should use. So you can't have a web with a thickness less than this value. For stiffened web, the value for stiffened web is different because stiffened web has support or some enhancement from the stiffener. So we have two types of stiffened web. The first one is transversely stiffened web, similar to here. So we have only the vertical stiffeners. So these stiffeners are transverse stiffeners. In this case, the thickness of the web for transversely stiffened web should be TW more than this value, D1 over 200 times root F yield over 250, when S over D1 is between 1 and 3. What is S? S is the spacing between transversely or transverse stiffeners. So S is the transverse stiffeners spacing. So you have S and D1 is the clear height of the web. So if S over D1 between 1 to 3, use this value. If S over D1 between 0.74 and 1, we should use TW more than S over 200 multiplied by F yield over 250. The third case, if S over D less than 0.47, sorry, 0.74, so we take TW more than D1 over 270 multiplied by root F yield over 250. So these are three cases of the web of uh, stiffened web, but stiffened web with transverse stiffness. So based on the dimension of D1 and S, you can decide the value of TW between the three. Okay? So this for web with transverse stiffness. The second part is stiffened web, or the second type of stiffened web is the stiffened web with both longitudinal and transverse stiffeners, similar to this one here. So this transverse and this longitudinal. So in this case, thickness of the web with set of longitudinal stiffeners placed on one or both sides of the web at a distance of 0.2 d2 from the compression flange shall be not less than these values. So if we consider this our moment, so the top flange is compression flange, the bottom flange is tension flange. So if we have the web stiffener at a distance 0.2 d2 from the top, where d2 is twice the clear distance from the neutral axis to the compression flange. So if we consider this is our moment, so let's assume this is our neutral axis. So D2 is twice the distance from the top flange or the compression flange to the neutral axis. So this, if we consider this, let's say it D3. So D2 equal to 2 times D3. Okay, if the beam under only moment, so D3 should be equal to D1 over 2. But I just give it, let's call it D asterisk instead of D3. Just to give it a different symbol. So it can be half. Okay, so if the neutral axis in the middle, So this should be replaced by d1 over 2. So it should be d1. So actually d2 can be in some cases equal to d1 and some cases it's not equal to d1 based on the location of the neutral axis. So based on this value, if the longitudinal stiffener at a distance of 0.2d from the compression flange, so this means the standard recommend to put the longitudinal stiffener close to the compression flange because we are worried about the buckling of the compression part, so it is better to, or it is preferred to be close to the compression flange. So in this case, TW, the whip, should be more than D1 over 250 multiplied by F yield over 250 when S over D1 between 1 and 2.4. Again, what is S? S is the distance between the transverse stiffness. So S is the distance between the transverse stiffness. So TW will be this value when S over D1 between 1 and 2.4, and TW we will replace D1 with S here when S over D between 0.47 and 1. The third one is TW more than D1 over 340 when S over D less than 0.74, where D2 again is twice the clear distance between the neutral axis to the compression flange. Okay, as another case here, the thickness of a web with an additional set of longitudinal stiffener placed on one or both sides of the web at the neutral axis shall not be less than. So if we add one more, if this is our cross section, so we have one set of the longitudinal stiffener here or here as well. So this one at 0.2D. If we have another neutral axis, I will just need to increase the size a little bit. So this was the first case of the standard. Second case, if we add one stiffener here as well at neutral axis, if we consider this our neutral axis, if we have additional set of stiffeners here, so in this case, the thickness of the web should follow this value. So the thickness of the web, T web, should be more than or equal to D1 over 400 root F yield over 250 when S over D less than 1.5. So the first case is for one set of longitudinal stiffeners. The second case is for additional set of longitudinal stiffener at neutral axis. Okay, so this was the arrangement of the web just to make sure the thickness of the web for unstiffened and for stiffened web follow these values. So the next one is, or the next topic as we mentioned, is the shear capacity of the web. The shear capacity of the web, because as you know, beams or girders are mainly under moment and shear. Okay, so moment we have designed for moment last week, and mainly flanges are carrying or resisting the moment. So moment is resisted by flange. The shear is resisted by web. That's why, again, we are focusing on the web in this class or this lecture. So for the webs, we have again stiffened and unstiffened web. So these formulas we are using now are for both stiffened and unstiffened web. So when we have cases the formulas are different, it will be separated to stiffened and unstiffened. So now a web subject to a design shear force should satisfy the following formula. V asterisk should be less than or equal to phi V V. V asterisk is the design shear, as we know. VV is the shear capacity of the web. So this is similar to any design formula. The design value should be less than the capacity, where phi is the capacity factor from table 3.4, and for steel members phi equal to 0.9 for steel members. If you are designing a steel member, so phi is equal to 0.9 for all cases. Phi has different value for connections. VV is the nominal shear capacity of the web determined using these two clauses. We will see them now. The first one is this clause. VV can be equal to VU, the nominal shear capacity of the web, where the shear stress distribution is approximately uniform. And this is our case. So our case, we are assuming that the shear distribution on the web is approximately uniform. If it is non-uniform, there is a different formula. So here, as you can see, VV equal to VU. U means uniform. So VU here is the nominal shear capacity of a web with uniform shear stress distribution. If we have normal shear stress distribution, we have two cases. So we already mentioned now in our course, we will be looking at uniformly distributed shear. So this means that we can write the formula here, V asterisk less than or equal to phi V U. So the first formula can be written in this form because we consider only the uniform shear in this class. So if we have a uniform shear, we have two cases. Case number one, when the maximum web panel depth to thickness ratio, d web over tw, satisfies the formula. So the shear capacity is impacted by or affected by the slenderness ratio of the web, which is dB over tw. So the depth of the web over the thickness of the web, which is the slenderness ratio, affecting the shear. The first case, if we have d over tw less than or equal to 82 divided by root f yield over 250. If the slenderness ratio of the web less than this value, so the shear capacity VU, or the shear capacity for uniform stress VU, will equal to VW, where VW is the nominal shear yield capacity of the web specified according to clause 5.11.2. So VW actually is the maximum shear capacity of the web. In different words, this means that if dB over tw less than this value, this means that no buckling will occur for the web. If we don't have buckling, so we will reach the maximum value we could reach for the web, which is VW. So VW is the shear yield capacity. So VW is the shear yield capacity because in this case, no buckling occurs. So no buckling occurs means that yielding occurs. So that's why we are considering VW. So VW equal to this formula here, VW equal to 0.6 F yield AW. F yield is the steel yield strength. AW is the gross sectional area of the web. Okay, so this formula AW is our only unknown or our parameter we should calculate to find VW. So any section with stiffened or unstiffened web cannot exceed this value for shear capacity. Okay. The second case, if T, dB or TW more than the value of 82 divided by root F yield over root 250. So this means that the slenderness ratio exceeded the value of 82 over root F yield. This means that buckling occur. Okay. If buckling occurs, so our, can you still see it? If buckling occurs, this means that our ultimate shear capacity VU, sorry, our uniform shear capacity VU equal to VB. VB here, instead of the yielding shear capacity, it is called the buckling shear capacity. So we expect in this case that the shear will be affected by buckling because buckling will occur before bending. Sorry, buckling will occur before yielding. Okay, so for unstiffened web, so now VB is different. VB has two values. VB for stiffened different from VB from unstiffened. So here we have separated the calculation. So VB stiffened different from VB unstiffened. So let's start with unstiffened. So VB for unstiffened webs, the buckling shear capacity for unstiffened web shall be calculated using the formula VB equal to alpha V times VW and should be less than VW. So this is our formula. Again, the maximum is VW. VW we calculated earlier as 0.6 F yield AW. So it will be portion of it or percentage of it. What is the parameter we should use? Alpha V. Alpha V equal to 82 divided by dB over T web root F yield over 250 squared. Okay, so alpha V depend on the slenderness ratio dB over TW. Okay, so this is the formula for alpha V for unstiffened web. For stiffened web, we have a different value for VB. VB will be using this formula here. So for stiffened web, VB equal to alpha V times alpha D times alpha F times VW and should be less than VW. So again, it is a percentage of VW and cannot exceed VW. VW is 0.6 if yield AW. So this is the formula for our stiffened web. So unstiffened web, alpha V times VW directly. Unstiffened web, we have alpha V, alpha D, alpha F. These are the formula for alpha V. Here, as you can see, it is different from the formula for unstiffened web. So we have, again, 82 dB over TW root a field over 250 squared multiplied by this factor here, 0.75 divided by S over dB squared plus 1 and should be less than or equal to 1 when S over dB between 1 and 3. So if S over dB between 1 and 3, this is our alpha V. So again, what is S? S is the transverse stiffener spacing. Okay, so this is S and the dB is the web height, web clear height or depth. Another formula, if S over dB less than 1. So if S over dB less than 1, the first term is the same. The second term, instead of 1, it is replaced by 0.75. And here 0.75 replaced by 1. So two differences here. 0.75 replaced with 1, 1 replaced by 0.75. So this for alpha V. For alpha D, it is 1 plus 1 minus alpha V divided by 1.15 alpha V root 1 plus S over dB squared. As you can see here, the parameter alpha D depend on alpha V. So you should find alpha V first and then find alpha D. So it looks like complicated, but the standard help us and give us the values of alpha V, alpha D together in table 5.11.5.2. So we don't need to find alpha V alone and then find alpha V because we will find alpha V times alpha D directly based on what? If you look to the table, how can we find the value of alpha V times alpha D directly? We need to find this ratio, the slenderness limit. So if you know the slenderness limit, for example, it is 160, and you know the value of S over dB. So we have this one here. And let's assume that we have S over dB in any value, for example, 1.5, 1.25. So our value will be this value. So for example, here, alpha V times alpha D equal to 0.721, and you can use this value. For alpha F, so we have, if you go back to the formula, we have alpha V, alpha D, okay, we can find them as one value from the table. For alpha F, we will take it as 1. So alpha F, the flanger strain factor, shall be taken as 1. There is a different, like other method for alpha F, but to simplify in our class, we will take it as 1. Okay? Any question about the shear capacity? Do you have any question about that? Any query? No? So to summarize the shear, we have two type of shear capacity based on what? Based on the slenderness ratio. So the first step to find the shear capacity is the slenderness ratio. Then if the slenderness ratio less than the slenderness limit of buckling, so no buckling will occur, so the shear strength will be equal to the shear yield capacity. In this case, VW equal to VU equal to 0.6 F yield AW. But if the slenderness ratio exceeds the limits, 82 over root, so buckling occurs. If buckling occurs, so we have two different sets of formula. One for unstiffened. Unstiffened, we have VB equal to alpha V VW, according to alpha V, this formula here. And we have stiffened webs, a different set, where alpha VB equal to alpha V alpha D alpha F VW. Alpha V and times alpha D come from the table 5.11.5.2, and alpha F equal to 1, so you can find alpha VB. Okay, so this is a summary of what we have done for shear. The next part is effect of bending or interaction of bending and shear. So again, we have the beam under V asterisk and M asterisk. When the beam under bending, this will affect the shear capacity of the member. So we need to consider the interaction of or the combination of shear and bending moments. There is two methods in the standard to consider the shear and moment interaction. We will consider the proportioning method. For the proportioning method, the bending moment is assumed to be resisted only by flanges. The design bending moment shall be satisfying M asterisk less than or equal to phi MF. So before, when we design the beam or consider the beam only under bending, it was M asterisk less than MS and MB. So here it become MF, where MF is the moment capacity calculated for flange alone and determined as follow. This means that in this case we ignoring the contribution of web in the moment. Okay, so it is like we ignore the moment the moment capacity comes from the web. So as you can see, the moment will be MF equal to AFM times DF times F yield. AFM is the lesser of the flange effective areas, for the compression flange and the lesser of AFG point, the lesser of between AFG and 0.85 AFN FU over F yield for the tension flange, where AFG is the gross area of the flange, AFN is the net area of the flange, DF is the distance between the flanges centroid. So if we have this section here, so only the flanges are considered for moment. So the distance between the two flanges centroid is DF. AFN and AFG is the area of the flange. AF gross and AFN. Okay, AFN and AF gross can be equal if we don't have bolts in this case. That will get easy to find. AFM is the lesser of flange effective areas determined using clause 6.2.2. So AFM is the effective area for the flange calculated before in the design in the design, or the effective area we calculated earlier in the previous lectures, and you can find it using the effective widths. This for the compression flange. For the tension flange, AFM for the tension flange will be the lesser of two values as well, AFG and 0.85 AFN times FU over F8. So we will consider calculating this one and then take the lesser. Okay, so we have like two flange. One of them is compression flange, one of them is tension flange. Okay, so we will consider compression flange using effective areas. For the tension flange, we will consider two values, AFG and 0.85 AFN, something like this. Then we will take the lesser between the compression flange and tension flange. Okay. Then after we found the moment, the modified moment, the shear capacity F asterisk, or the shear design formula should be V asterisk less than phi V VM, where VVM equal to VV, and VV is the nominal web shear capacity determined using the previous calculation. So this means we will calculate the shear normally as before, but what we will change or what we will check is the moment capacity using the flanges only. Okay, so this is the idea behind this method. So we ignoring the whip in the moment so that the flange will carry a whole moment and the whip will carry whole shear. This is the logic behind this method. Okay, any question guys about that? Any question? Okay, can we have a break for 9 minutes? We can meet at 10, meet back at 10:05, or let's make it 10 minutes. So we meet at after 10 minutes from now. So see you at 10:07. Okay. Okay, guys, can we continue now? So, are you here? I think it's better. Okay, so after we learn how to find the shear capacity of the web, stiffened and non-stiffened web, now we will look at the bearing capacity for webs, stiffened and unstiffened web. The first thing is the bearing capacity. We have the load applied to the flange. Like if we look to this one here, so let's add a new slide. So if we have side elevation to the section, to our cross section, and this is the elevation itself. So we have load applied to the flange. So this load will transfer through the flange to the web, and then we need to know what is the slope or how the load is dispersed through the flange or the web. So the standard give us how the forces are dispersion to the web from the top flange. So where a force is applied to a flange, either as a buoyant load or through a stiff bearing length, BS. So BS, if the load is distributed over a bearing plate, it shall be assumed to be dispersed uniformly through the flange at a slope of 1 to 2.5. So this is the first part here in the flange because it is not very thick. So the load will be transferred using a slope 1 to 2.5. So this for flange. To the surface of the flange as shown in this figure, or to the top of the flat portion of the web for rectangular and square hollow section as shown in other figure. So we are only focusing on flange and web sections, which is I-beam or C section. The stiff bearing length is that length which cannot deform appreciably in bending. The dispersion of the load to the flange shall be taken at slope 1 to 1. So we have another slope through the solid material as shown in the figure. So after the load transfers through the flange using slope 1 to 1 to 2.5, in the web it will take a different slope which is 1 to 1. So 1 to 1 in the web and 1 to 2.5 to the flange. Okay, so the way the load start from distributed over a BS on the top flange, and then it transferred to the web to a width of BB. BB is equal to BBW, which is the slope horizontal projection for the web, and BBF is the slope horizontal projection for the flange itself. Okay, this for interior force, so we are not close to the edge. If we are close to the edge, if you can see here, the other case, how the load transfer, if the load close to the edge, like support or a load to the edge, the load starts from BS, then again, through the flange, it takes the slope 1 to 2.5, so similar to before. But here for the web, what happened to the web in this case? there is no room to go outside the beam, so that's why it stopped here. So this is BO. BO is the edge width, and the remainder is the same. So for the inner side, it's already go again 1 to 1, and it has a distance until reaching the neutral axis. Okay, but here on the left side, we don't have room because it will go outside the beam. So anyway, the total width of distribution of the load at the neutral axis, BB, here BB equal to BW, BBW twice plus BBF. Here we have another term or a new term, which is BO. Okay, so this just indication how the load is dispersed through the flange and the web until reaching the neutral axis. Okay, and let's have a look on this statement again. Again, the dispersion of the load to the flange shall be taken as slope of 1 to 1 through solid material as shown in figure 5.13.1.1. So this is how to find sorry, the width of the bearing. So if the beam, I received a question about stiff bearing. Stiff bearing means the plate we have when you apply the load here to this one here. Okay, you can't just apply the load directly. You should have a bearing plate to distribute the load. So for example, we add a plate like that. So this plate should be stiff enough so that it doesn't bend if we apply the load on it, on top of it, so it doesn't bend. Okay, so stiff plate is there to distribute the load. Otherwise, it will cause local buckling because we have concentration of load. Okay, stiff plate means it doesn't bend due to load. Okay, so it is strong enough to distribute the load without any bending. Is it clear now? No, it's so this diagram here just to give us hint how to find the stiff bearing length, which is BS. So BS is the stiff bearing length. So if we have a beam like sitting on another beam like that, so we will consider BB as we take 1 to 1 and 1 to 1 here from the fillet weld so that we have BS like that. Okay, this from one side and this from, if we look it from the side here, so this is our view. So if we look AA, for example, here, so this is how AA looks like. Okay, so this is how to find BS. And now let's look to the formulas for the bearing capacity of webs. So the bearing capacity of webs, if it is stiffened or unstiffened, again, similar to shear capacity, we have some formulas general for stiff and unstiffened, stiffened and unstiffened. Then we when we have different cases, we will separate them. So the bearing capacity R, the bearing force R asterisk should be less than phi R B. So again, the design force should be less than or equal to phi times the capacity. So this is the design bearing force, and this is the bearing capacity, and phi equal to, again, 0.9 for all steel members. So this is our formula for bearing capacity, where RB is the nominal bearing capacity of the web under concentrated or batch loading, and shall be taken as the leisure of its nominal bearing capacity RBY, or its nominal bearing buckling capacity RBB. So for RB, it has two values, one for yielding and one for buckling. For yielding, it is B RBY, for buckling it's RBB. So again, we have two values, yielding and buckling. So when to find yielding value and when to find buckling value, we will see now. So bearing yield capacity, the nominal bear yielding capacity RBY of a web shall be calculated as follows. RBY equal to 1.25 BBF multiplied by TW multiplied by F yield. So this is our formula for yielding bearing capacity. Do we have more value, more than this, or I mean RBW more or RBB? RBW is the greatest or the largest value of bearing capacity we can have. Okay, so when no buckling expected or when no buckling happen, RBY will be more than RBB, where BBF is the bearing width as shown in figure 5.13.1. This 5.13.1. So BBF is here. So BBF is BS plus 5 T flange. Okay, so this is the value of BBF because we have BS plus 2.5 T flange from left and 2.5 T flange from right. So BBF equal to BS plus 5 TF. TW is the width, F yield is okay. So again here BBF is BS plus 5 T flange. So we will calculate RBW. This is the bearing yield capacity, and then we will calculate the bearing buckling capacity. But the bearing buckling capacity will only calculated for unstiffened web. What this mean? This mean for bearing, we have two values, RBY yield and RBB for buckling. RBY is for stiffened and unstiffened webs. Buckling only for unstiffened web. So this means if you have stiffened web, the buckling, the bearing capacity is only one value, which is RBY. So we don't have option for, because no buckling expected if you have stiffened web. But for unstiffened web, we should have two values, R and RBB. So and don't forget phi, so we have phi RB and we have phi RBY, phi RBB. So buckling can be calculated for unstiffened web, but not for stiffened web. Okay, so for unstiffened web, we will calculate the bearing buckling capacity because we expect buckling for unstiffened web. How to find RBB? RBB will be considered as axial loaded member that we designed in the early lectures, week 2, in section 6. So RBB, we will consider the web as axial loaded member. Okay, so it is axial compression capacity determined according to section 6, but we have some modification. The modification are, we will take alpha B for this section as 0.5, Kf equal to 1, area of web or area of the section is T web times BB, where BB, if you go back to the diagram, where is BB? BB is this value here. So BB is the total total distribution width of the load at the neutral axis. So okay, so T web here or area of web here is T web times BB, where BB equal to B flange, just to get the correct symbol. BBF plus 2 BBW. So B equal to BBF plus 2 BBW. Okay, so we will consider it as axial loaded member, and we will follow the procedure of section 6. So if you remember, for section 6, we have two loads or two criteria. One of them is the section capacity. One of them is the member capacity. So for the section capacity, we have NS equal to KF times AN times F yield. For the section, for the member capacity, NC equal to alpha C times NS and should be less than or equal to NS. So we will follow same procedure to find the section capacity and member capacity, but the only change is we need to use this data here for the web. So alpha B taken as 0.5, KF taken as 1, area web equal to T web BB, where BB is BBF plus T BBW. Okay. Do you have any question about this part for bearing? So the bearing, we have two cases, one of them yield, one of them buckling. Yield can be calculated for stiffened and unstiffened. So this formula, RBY equal to 1.25 BF times TW times F yield. This for both stiffened and unstiffened web. But for the bearing buckling capacity, it is only for unstiffened web because we don't expect buckling for the stiffened beam or the stiffened web. Okay, any question about that? No? Okay, so now after we check the web for shear and interaction of moment and shear, and we design or check the bearing capacity of the stiffener, the next part is how to design the stiffeners. So we have or different type of stiffeners. The first one is the load bearing stiffener. So the first information we should know how to fit the load bearing stiffeners. So the load bearing stiffeners should be added to the beam at the loading or the reaction points. So a load bearing stiffener shall be fitted to provide a tight and uniform bearing against the loaded flange unless welded are provided between the flange and stiffener. So if we just add add something here. So if this our I beam or our section. So if we have load somewhere here, we should add stiffener. So this stiffener is added at the area of the load and provide enhancement to the flange to resist this load or to transfer this load, whatever the width is, but we need to have load bearing stiffener. This load bearing stiffener, as you can see, should be fitted to provide tight and uniform bearing against the loaded flange. Okay? Unless welds are provided between the flange and stiffener for the purpose of transmitting the concentrated force or action. Where a point of concentrated force is directly over the support, this provision shall apply to both flange. So if you have a reaction or support, so you should apply this to both flange, not only the loaded flange. Okay? So the first check or the first design requirement is the yield capacity of the stiffener. We have two criteria of design again, buckling and yield capacity. So we have yield and buckling capacity. For the yielding capacity for a stiffener, for a load bearing stiffener, R asterisk should be less than or equal to phi RS yield. So R asterisk again is the design bearing force or the design reaction applied to the flange. Phi is the capacity factor, and we know phi equal to 0.9. RSY is the nominal yield capacity of a stiffened web. So it will be RBY plus ASF yield S. So RSY equal to RBY plus AS times F yield S. What is RBY? We calculated earlier in the web. If you remember, it was 1.25 BBF multiplied by TWF yield. So this for the web, and the other term is for what? This one for the stiffener itself. Okay, so it is like both the web and stiffener become one unit, and the capacity of the stiffener come from both together. So RBY, as we mentioned, is the nominal bearing capacity. AS is the area of the stiffener. F yield S is the yield strength of the stiffener. So these are the formula to consider the yielding capacity of the stiffener. The second one, or the next criteria for bearing stiffener design, is the buckling capacity. So for buckling capacity, we have again R asterisk should be less than or equal to phi RSB. So for stiffener, we have R asterisk should be less than or equal to phi RSY and phi RSB. Okay. So this is our formula where again phi is 0.9 for all member in steel, and RSB is the nominal buckling capacity of a stiffened web determined in accordance with section 6, where we have used alpha b equal to 0.5, kf equal to 1 for the compression member whose radius of gyration is taken about the axis parallel to the web. So RSB here will be again calculating for axial loaded web and replacing all the factors as before with alpha b equal to 0.5, kf equal to 1, and use section 6 to find the value. The effective section of the compression member shall be taken as the area of stiffener together with the length of the web on each side of the center line, not greater than the lesser of these two values. So 17.5 TW divided by root F yield over 250 and S over 2. Again, S is the stiffener spacing. Okay, so when we are calculating the effective area for the stiffener or the effective section for the stiffener, the area of stiffener together with the length of the web on each side of the center line not greater than the letter of these two. So we will calculate the lesser of these two, and the area should be less than these two. So if we interpret this here, so you have the lesser of 17.5 TW divided by root F field over 250, and the other one here is S divided by 2. Okay, so we should be not greater than, mean less than or equal to. So the effective section in our axial load calculation shall be taken as the area of stiffener together with length of web on each side not greater than the lesser of these two. Not greater than the lesser of these two. Okay, then what is the next step? The effective length LE of the compression member used in the calculation of buckling RSB shall be determined as either of two values. L effective is 0.7 D or L effective is D, where so it can be taken as 0.7 D1, where the flange are restrained by other structure elements against rotation in the plane of the stiffener, or can be taken as D1 if either of the flange is not so restrained. So L effective will be taken as 0.7 D1 if we have restraint from other member. L effective equal to direct D1 when we don't have restraint. Okay, so this is the effective area, and LE has two values as well, 0.7 D1 and D1. We have restraint, and if we don't have restraint. Okay, the last parameter of the design is the width of the stiffener, or the outstand of a stiffener. Unless the outer edge of a flat stiffener is continuously stiffened, the stiffener outstand from the face of the web BES shall satisfy the following: 15 TS divided by F yield S over 250, where TS is the thickness of stiffener, F yield S is the yield strength of the stiffener. Okay, what this mean? If we have again the cross section, we may have stiffener that go like that outside of the flange. Okay, the width of the flange, oh sorry, the width of this part is called BS. BAS is the is the outstand stiffener from the face of the whip. So this is the face of the whip we are talking about, and this is BAS. So BAS will be less than or equal to 15 TS divided by F yield S over 250 under the root. So this is the thickness of the this is the thickness of the stiffener. So TS is the thickness of our stiffener like that. Okay, so the stiffener cannot go more than BES, where BES is 15 TS and divided by root F yield S over 250. Do you have any question about that? These are dimensioning of the outstand of the stiffener. So the previous one, the previous design was for load-bearing stiffener. Now we will look at the intermediate transverse web stiffeners. Intermediate transverse web stiffener means it is not a load-bearing stiffener, so no load at this area or at this point. So intermediate load stiffener, web transverse web stiffener shall extend between each flange and shall terminate no further from a flange than 4 times of the web thickness. What does this mean? So again, if this our section, so if we have this is our section. So the intermediate stiffener doesn't need to be at or under the load. Okay. And the standard mention, if we look to the elevation, this stiffener can stop, doesn't need to reach the flange. So it can be something like this. Okay. How much this distance is, or what is the maximum distance is, if you look here. So the stiffener shall terminate no further from a flange than 4 times the web thickness. So this cannot be exceeding 4 T web. So if this our T web, so this distance cannot exceed 4 T W. Okay, so this is what is meant by the internal stiffener and the intermediate stiffener, and where we can stop it. Intermediate stiffener can be also provided on one or both sides of the web. So you can put it on one side like this, or you can put it on both sides. So the first requirement of the standard is the minimum area of the stiffener. What is the minimum area of stiffener? Intermediate web stiffener not subjected to external load or moment shall have an area of AS. AS should be all of that. So the area of stiffener more than or equal to 0.5 gamma AW 1 minus alpha V asterisk over phi VU multiplied by S over dB minus S over dB square divided by 1 plus S over dB square under the root, where alpha V is the shear buckling coefficient for the web we have determined earlier for stiffened web. So alpha V for stiffened web as before. Gamma can be taken one for pair of stiffeners and 0.8 for single angle stiffener and 2.4 for single plate stiffener. So we have single angle and single plate, 1.8 and 2.4. So if you have stiffener from both sides or pair of stiffener, alpha is 1, 0.8 if it is single angle, or 2.4 for single plate. Okay, so gamma is okay, alpha V is okay, AW is area web, V asterisk is the design shear, V ultimate is the shear capacity, S is the spacing, dB is the uh, clear depth of the web. So all the parameters are known except for gamma and alpha V. Okay, so this is the area, minimum area, and the design criteria for the transverse, intermediate transverse web stiffener. We have only one criteria for this one, which is buckling capacity. So no yielding expected for this one. So we don't expect that the stiffener will reach yielding in our design. So for intermediate stiffener, V asterisk should be less than or equal to pi multiplied by RSB plus VB. Phi, as before, 0.9. VB is the nominal shear buckling capacity specified earlier for stiffened web using alpha D equal to 1 and alpha F equal to 1. So if we go up to the shear, V is shear. So this is the formula we have for VB. So this is our VB. So VB is alpha V, alpha D, alpha F, VW. So if we go back to here when we are designing the intermediate stiffener, so we know that alpha we know that VB equal to alpha V alpha D alpha F times VW less than or equal to VW. So we will replace alpha V, sorry, alpha D with 1, alpha F with 1. So this will be 1, this will be 1, and you need to find alpha V for stiffened web. Alpha VW already we know, 0.6 F yield AW. So you can find VB, and what about RSB? RSB is the nominal buckling capacity of the intermediate stiffener determined in according with 5.14.2. So if we go up a little bit here, here is the value of RSB. So we need to find RSB according to this formula here as an axial loaded member. So RSB will be calculated as axial loaded member as before. So what you understand from this formula here? This is my question for you. the capacity of, or the buckling capacity of transverse web stiffener is controlled by what, or limited by what? What do you think? We have two components. One of them is RSB, one of them is VB. What this mean? This means that we have a combination of bearing and shear. So the intermediate transverse web stiffener is designed to resist both bearing and shear, and so the capacity of this member will be a contribution or a combination of the shear and bearing capacity. Okay, is that okay? And the last parameter here is the effective length, L effective of the compression member used in RSB will be taken here as D1. So we will take it as D1. Okay. Okay, so this is the topics we need for this lecture, the bearing and shear and combination of bending and moment, moment and shear. Here is some for your information, some data or some uh, checks for your information. We will not use in our assignment or our test, but if we look here, this is section I or appendix I in the Australian standard. So in this appendix, it gives us how to check or how to design a stiffened web under combined action. So for stiffened web under combined action, we can have different type of action on a stiffened member. We may have axial load. We may have shear. We may have moment. And we have bearing. So this member is under all the possible action at once. So the formula, we have two checks again, one for yielding check and one for buckling check. So this is the check for members for stiffened member under all type of loading, bending, shear, axial, and bearing. So we have M, V, N, and R. So if you have all the possible loads or all the possible actions at once, so the formula to check is this formula here. So this formula is for yielding check. So as you can see, we have bearing. This is reactions, the reaction over 5VB, 5BBF, TW, and so on. So this is the formula. It is a little bit complicated one. I mean, too many parameters, but this check may be needed after finishing all the design. So if you want to check the suitability of the section under all the load combination, or sorry, under all the combined loading together, so you need to refer to this formula here or section I.1. Okay, this for your knowledge only. So that's why I will not stress too much on it. For the buckling check, so we have another formula for buckling. So this formula is directly checking R for the bearing load N is the axial load, V is the shear load, and M is the moment. All of this should be less than or equal to 1, and all the parameters are defined here. So VV is the nominal shear capacity, MW is the nominal moment capacity of the web, RSB is the nominal buckling capacity of the transverse web, and all the required parameters can be found here. So this to check is only for stiffened web. One of them is yielding check, one of them is buckling check. This check is for combination or a combined loading of all the possible straining action, moment, shear, axial load, and bearing. Okay? Do you have any question, guys, about our lecture today? Any question? No? Okay. Thanks all for attending, and I will see you in few minutes in the class. Thank you.